Now let us look at some of the examples of this single object allocation mechanisms to understand the implications of the Myerson's result better. So the first two are quite standard and we have discussed it quite a few times. The constant allocation rule. So it is of course non-decreasing and the payment could be any constant. For example, it can be equal to 0. The second allocation rule is the dictatorial rule. You give the object only to one of the agents who is a dictator, and it is definitely going to be non-decreasing. For him it's always 1, for everybody else it's always 0. The payment again can be some constant value or could be 0. So these are trivial mechanisms. Let us now come back to this second price auction. We have actually seen this in the beginning of the previous module or maybe a few modules before. Now the payment that we have seen from the Myerson's characterization result has this following form. Let us suppose that this first term pi0 of t minus I is equal to 0. Then all that you have in the rest of these two terms in this expression is fi ti t minus I, and we know that in the second price auction there would be a kind of a step function like behavior. So holding everybody else's type fixed, if player i's type increases, then till certain point it does not win that object because its valuation is not the highest, and the moment it becomes the highest valuation, it starts becoming the winner. So the allocation rule would look something like this. The type keeps on increasing, and the moment it is just above the type, the second highest type, so the maximum valuation of all the agents except agent I, that is the threshold after which it starts getting the object for sure. Before that it is not getting the object at all. So that is the fi tit minus I in the context of second price auction. Now the payment, if you look at it, what is going to be the payment? So this ti, so if you look at the first term here, this is ti multiplied by fi of tit minus I. So at this point it is 1, so therefore the first term is essentially this whole rectangle here. This is the area, and the second part is just taking the integral, so the area under this curve. So because before this it was 0, so it will be only this green region here. That is the second part. So if you take the difference of the whole rectangle minus this green region, what you are left with is this part, the red region, which is the payment part. And that is essentially nothing but, because the height of this is 1, so it is nothing but the second highest bid. So this is the second, so the payment itself is the second highest bid, which is the second price auction. So Myerson's mechanism is giving you the victory auction as a special case. Now you can also generalize this a little further. So you have an efficient allocation, but now you are selling it with a reserve price. So this is also a non-decreasing allocation rule. You can verify that once the type increases, keeping everyone else's type fixed. After a certain point, which can be the threshold point, instead of just being the t minus I2, it will be the maximum of this t minus I2 and the reserve price. So what is a reserve price? So it says that if the highest value is below a reserve price R, then nobody gets the object. So that is the minimum selling price at which the auctioneer will sell this object. Otherwise the item goes to the highest bidder. So if there is at least one individual who is above that value, that reserve price value, then among those players who are above that reserve price, then it will proceed as if the usual allocation rule. Whoever is the highest bidder, he gets the object. Now the payment is essentially the maximum of these two things, the second highest bid and the reserve price. So if it turns out the second highest bid is actually smaller than R, then the winner is asked to pay that reserve price. So that is the modification, and this can also be seen as an outcome of the Myerson's rule. I mean, simply because of the fact that the allocation rule, this threshold will now be replaced with max of t minus I2 and that reserve price R. So everything remains the same. It will actually be the payment will be this. So that is also a special case of the Myerson's characterization result. Now these are all standard things, we can in some sense relate to it, but there could be very weird allocation rules which are also implementable by the results of Myerson. So let us look at one such case. This gets a little messy, and we really cannot build a lot of intuition about it, but the whole point is this kind of a mechanism can also be DSIC. So what is this mechanism? You have, suppose, two players, and there are three allocations that are possible. Either the object goes to player 1 or goes to player 2, or it is not allocated at all. The object is unsold. Now suppose the type profile is given by this T, which is T1 comma T2, and the seller computes the following thing. It tries to find out which of these three things are actually maximum. So one is the constant, which is 2. The second one is the square of the type of the first player, and the second one is the cube of the type of the second player. Now it selects these three allocations, one of these three allocations, depending on which of these values are the maximum. So whether 2 is the maximum among this max, or T1 square is the maximum, or T2 square is the maximum. Of course, the ties can be broken in some arbitrary way. So in this case, we are assuming that this is breaking the tie in this favor. Now you can actually do a very similar kind of analysis to find out what will be the allocation. So this is going to be a very similar thresholding kind of thing. So when the player player 1's, so this will be player T1. So when T1 is actually larger than the square root of the max of 2 comma T2's cube, when T1 is the maximum of all these things, then it goes to player 1. If T2 is actually larger than the cube root of this max of 2 comma T1 square, then it goes to player 2. But you can see that both of these are monotone. Essentially both of these are kind of threshold functions, the step functions, with this the threshold being this value. Anything above that, that player wins, and anything below that, that player loses. And at that point, exactly at that point, the ties are broken in this way. You can also compute the payment rules, which are actually going to be the value itself, this value itself, because in that case, this threshold value that we have written here will be replaced by those corresponding values. So even though this might not have any intuitive meaning, we cannot really relate to something, some auction. This is also an auction which is implementable, and there exists a well-defined payment formula which will implement this allocation rule. That is given by the Myerson's result. Let us now discuss the property that we have also seen in various other contexts, called the individual rationality. We are going to call a mechanism f comma p to be exposed individually rational if the utility of this player is non-negative at every type profile and for every player. Now, why are we calling this as an exposed? Because this is being satisfied for all ti and t minus I. So even though the agents could see the other players' types, and that is after the game is over, everybody sees everybody's type, it is still beneficial for them to participate in this game. So that is the exposed individual rationality. Note that this is much stronger than interim or ex ante individual rationality. Even if something is exposed individually rational, of course it is going to be ex interim or ex ante individually rational. Now we are going to present a result which gives some sort of a structure on that constant function. So remember that the payment formula that we have discussed. So this is the payment formula of the Myerson's characterization result. It had this constant function which is sitting at the beginning, pi0 t minus I. Now at certain points we have actually used certain values, so it can have any constant value. But whenever we are imposing individual rationality, the following lemma will actually show that it has a very specific structure. So it says that when this mechanism f comma p, if that is DSIC, then it is going to be individually rational if and only if for all the players and for all the types of the other players, this pi 0 t minus I is at most 0. So it cannot be positive. So this is the first result, first sub result of this lemma, and it is going to be individually rational and satisfies no subsidy. That is, the payment is always going to be non-negative. So nobody is actually getting paid by this mechanism. Everybody would be paying because this item is getting allocated. This will happen, this condition will get satisfied if and only if for all these players and for all the t minus i's in capital T minus I, the payment is actually equal to this pi 0 comma t minus I is equal to 0. This constant is going to be equal to 0. Because of this property of individual rationality, we can actually pin down, we can actually make sure that this this constant function also satisfies certain properties. So let us try to prove the first part of this lemma. So let us look at the forward direction, that it is individually rational. So if it is individually rational, then we know that even for this zero valuation, it is going to be satisfying this inequality for every ti, including ti to be equal to 0. So that automatically gives this inequality. But in the reverse direction, if we assume that this is non-negative, then we can actually write the utility of player I by expanding out this payment for player I given by this Myerson formula. So we notice that this particular term is going to get cancelled. So this appears both as the valuation of player I, expected valuation, and also it appears in the payment expression. For the rest of the things, we know that this fi is non-negative. This is just an allocation, so this is a probability. Of course, it has to be non-negative. So this term is actually non-negative, and because of the fact that pi 0 comma t minus I is non-positive, so therefore this minus of that will be non-negative. So together this is always going to be non-negative. So that proves both the necessary and sufficient directions for case 1. For part 2, we will have to show that this individual rationality along with no subsidy happens if and only if this constant becomes equal to 0. So what happens here? So individual rationality tells us from the previous result that it is going to be non-positive, and if we are involving this result whenever we are imposing no subsidy, that is pi of ti t minus I is always non-negative, that means that this is going to hold for all ti. We can put it to be equal to 0, and therefore this is always going to be non-negative for that ti, which is 0. So together pi 0 ti is both non-positive and non-negative, therefore it must be equal to 0. And the other direction, that is when this is equal to 0, it's very easy to see that it is individually rational because of the previous result, and no subsidy. We can just look at this expression here, the payment formula essentially. This payment formula is always going to be, so this actually disappears because this is 0. This term is essentially the area subtended by that curve on the y-axis, and that is always going to be positive. So therefore the payment is always going to be non-negative, so it is a no subsidy mechanism. Okay, so that was two implications of the property individual rationality on this constant factor. This will be useful when we actually try to prove some characterization result later on. In the remaining part of this module, we are going to look at some non-Vickrey auctions, And the purpose of discussing these examples is to focus more on the budget balance part. So we have seen this in the context of VCG mechanism, that the payments may sum to something larger than zero. One of the objectives was to make sure that the sum actually goes down to zero. The sum of the payments collected from all the players are equal to zero. Let us see in the context of Myerson's option, can we satisfy that property? So this is a little different, unusual mechanisms. So in this thing, the allocation is still similar. The object goes to the highest bidder, but the payment is such that everyone is compensated some amount, and that can be done by appropriately choosing this constant function, which is pi 0 comma t minus I. So how is this implemented? The highest bidder and the second highest bidders are compensated 1/n of the third highest bid. So what does that mean? So let's say, without loss of generality, the natural ordering 1, 2, 3 are in the order of their relative largeness of their types. So player 1 is the highest bidder, player 2 is the second highest bidder, and so on. So both these two players, their pi 0 t minus I will be equal to minus 1 by n times t3. And for everybody else except this first and second highest bidder, they get 1/n of the second highest bid. What does it mean? So this will be so pi 0 comma t minus I will be minus n of the second highest bidder. So everybody else will essentially get the minus 1 by n times t of 2. This will happen for all the players except player 1 and player 2. So now we can actually calculate the total payment. So we know that agent 1 pays, so this is the first term, that is the p1 0 comma t minus 1. And then we can actually write down what happens for this part. So this is the t1 times the allocation. So because player 1 is the highest bidder, he gets this object. So t1 times 1, this is the first term. And then you have this integral here. So you know that between 0 and t2, the agent 1 does not get that object. After t2, it is going to get that object. So therefore, this integral will give you. So this integral will be t1 minus t2. Now that actually cancels out t1, and all that you are left with is this expression. For player 2, it is only going to be the third term, because he does not get his allocation is so his allocation is always 0. So therefore, he does not get any additional payment here. So the other terms actually disappear. For all the other players, as we know, that it is going to be minus 1 by n times t2. So if we sum all these things up, all that we get is it is going to be 2 by n times t2 minus t3. Now this is going to be a positive term because t2 is larger than t3. But we can see that when the number of players increase, this total payment would be arbitrarily small. So for very large amount of population, the total payment collected by the mechanism designer is arbitrarily small. So this is almost budget balanced. Now this is a deterministic mechanism where the allocation is fixed. So it is still the highest bidder gets the object, but the payment is a little different. But let us now look at a mechanism which does a randomized allocation of this of the object. Unlike the previous mechanism where we were deterministically giving the object to one player, in this case we are allocating this object probabilistically. So to the highest bidder, it is allocated with probability 1 minus 1 by n. And the second highest bidder gets that object. It also has a very small probability of getting that object, which is 1 by n. Now here we are going to assume that this pi 0 comma t minus I is minus 1 by n times the second highest bid in tj, where j is not equal to I. That means that for player 1 it will be minus 1 by n times t3, which is the second highest bid, except that player. For player 2, it will be again say, the third highest bit, that is minus 1 by n times t3. For all the other players, it will be minus 1 by n times t of 2. So this pi is essentially the same as we have seen in the previous case. So let us now consider what will be the payment, because now the allocation rule has changed slightly. Instead of giving the object to the highest bidder, it is giving that with probability 1 minus 1 by n, and giving the second highest bidder with probability 1 by n. So if you now calculate those expressions, the payment according to the Myerson's payment rule, the first term will be minus 1 by times t3 for player 1. The second term is t1 multiplied by what is the probability that player 1, being it is the highest bidder, wins, that is 1 minus 1 by n. Now the integral can be broken up into two pieces, because when player 1 is within this interval t2 to t3, there it is the second highest bidder, but it has still a small probability of winning that. So therefore it will get multiplied with that probability. And again, between t1 and t2, it is having a probability of 1 minus 1 by n of winning that object. So together this is going to be this expression. So 1 minus 2 by n times t of 2. That is the payment that player 1 will make. Now player 2, if you do a very similar calculation, you will find that this is going to be equal to 0. And for all the other players, because they are never the winner, their thing is going to be minus 1 by n times t2. Now if you want to do it, so if you do this, the sum of all these terms, so this is t2, for player 2 it is 0, and for all the other players, n minus 2 players, it is going to be so n minus 2 times minus 1 by n times t2. If you take that sum, it is always going to be equal to 0. So just by changing the allocation from a deterministic allocation to a randomized allocation, what we could achieve was to ensure that the mechanism is budget balanced. Still it is actually following this monotone rule. So this object allocation is following a monotone allocation rule, and therefore this is going to be truthful. And the Myerson payment ensures that this implements this allocation rule, but this is also budget balanced. So that is a very important thing that we can see here. So okay, so with that we'll close this module. The purpose of this module was to show you some examples of the implications of this Myerson's characterization result.